Building an AI agent on your laptop is relatively easy. You install some libraries, drop in an API key, and it runs. But taking that same autonomous logic and deploying it into a governed enterprise environment like Databricks is a unique engineering problem. The moment you move to production, you run into governance layers. You have to manage how data persists over time, establish clear trust boundaries for code execution, and orchestrate complex handoffs between different systems. You cannot simply drag and drop an agent's raw Python script into a cloud workspace. That approach bypasses security protocols, ignores infrastructure limitations, and breaks compliance rules. The solution is to leave the agent's core logic untouched, but wrap it in a layer of Databricks native infrastructure that handles all the platform requirements. Operating within these limits requires a structural boundary, one that decouples the agent logic from the deployment plumbing. This brings us to the core, separating the skill from the harness. The skill is a portable directory with a markdown manifest and pure Python code. The harness is the Databricks infrastructure that wraps around the skill, handling Unity catalog, APIs, and serverless compute. This boundary serves a specific purpose. The harness absorbs all the platform friction, so the skill code can remain read-only and unmodified. Data moves through this system in a strict bucket-in, bucket-out pattern. Raw documents enter through Unity catalog volumes, get processed by serverless LLMs inside the harness, and the final artifacts land in governed consumption volumes. By enforcing this strict separation, data scientists can write portable code locally, while platform engineers maintain control over security, cost, and infrastructure. The first technical challenge in this architecture is deployment.
We need a way to get the skill code into the Databricks execution environment without bundling it into rigid deployment artifacts. We solve this using a mirror strategy. A publishing script maps the local file tree directly to a managed Unity catalog volume. It's a strict mirror. If a developer deletes a file locally, the pruning function instantly removes the orphaned volume file. Moving code like this introduces a vulnerability. We must ensure local environment artifacts do not corrupt the serverless execution environment. The publishing script handles this by explicitly blocking artifacts like _pycache folders and compiled binaries from crossing the boundary. Once the clean files are mirrored, the runner dynamically imports the skill code directly from this volume at runtime using Python's import lib. Because the workspace executes whatever Python files reside in that volume, the volume itself becomes a code execution trust boundary. To secure this boundary, write permissions to the volume path must be limited to authorized developers or automated service principals. The mirror strategy creates a secure, idempotent system. You publish a skill once to the shared volume, and any job across the workspace can reuse it without redeploying the surrounding infrastructure. Once the code is securely trusted and successfully executing, the next major friction point inevitably emerges at the storage layer. Consider a generative task where the agent needs to build a binary PowerPoint presentation using a library like Python PPTX. Unlike standard hard drives, Unity catalog volumes only support sequential writes, acting like a strict one-way conveyor belt. PowerPoint zip archives must seek backwards while building. Attempting this reverse movement on the volume instantly fails with an OSE error ERN05. We resolve this using the harness adapter layer. It initializes an in-memory byte buffer as a staging ground where the zip archive builds and organizes freely. Once fully constructed, the adapter executes a single atomic write, pushing the completed presentation seamlessly. Abstractions inevitably leak at the storage layer. The adapter absorbs that complexity, ensuring the skill logic remains perfectly agnostic to underlying hardware constraints. Now we scale from a single task to a pipeline. Imagine an upstream document analysis skill that needs to pass its output to a downstream presentation building skill. Serverless compute functions are inherently stateless. The downstream task has no automatic context of what happened in the previous step or where the files are located. To bridge this, we use manifest chaining. The upstream task writes a manifest.json payload with the file path and an OK status. To prevent collisions, these manifests are written to a run-scoped directory path using a unique job run ID. This manifest system also acts as the control mechanism for data governance. Before executing any skill logic, the harness runs a content guardrail to check the input document for PII or unsafe material.
If the LLM guardrail detects a violation, it intervenes immediately. The upstream task quarantines the flagged input, writing a rejected status. The original document is routed away from the main pipeline into a dedicated rejected volume, a dead letter queue. When the downstream task reads this rejected manifest, it knows to abort its execution. It cleanly skips the presentation build process. By handling the rejection through state metadata rather than a hard error, the job finishes successfully with a zero exit code instead of crashing, and the flag data is preserved for auditing. Manifest chaining provides both the map between stateless tasks and the circuit breaker, enforcing rigorous safety guardrails across asynchronous, distributed agent pipelines. With all these components connected, we have a governed pipeline. Inputs filter through guardrails, process via serverless compute wrapped in the harness, chain together using manifests, and land in structured volumes. However, running this architecture at scale creates an operational byproduct, a continuous accumulation of run-scoped manifest directories within the output volumes. To maintain system health, we deploy a volume janitor utility script built on the Databricks SDK. It executes an age-based logic check across the volume structure, targeting artifacts older than a threshold, safely deleting stale outputs and empty run directories. True production architecture must include its own self-maintenance. This automated cleanup ensures that our state management tools never degrade into storage liabilities. The core achievement of this architecture is the frictionless separation of concerns. Data scientists are free to focus exclusively on pure Python, prompt engineering, and deterministic logic. They never have to write cloud plumbing. Platform engineers, in turn, retain control over API gateways, volume access limits, and state management infrastructure. The enterprise perimeter now functions as a reliable engine for processing agentic workflows. Deploying enterprise AI requires shifting focus away from foundation models toward engineering a decoupled infrastructure that allows them to operate safely at scale.